Welcome back to Water Resources. This is the second lecture in the groundwater module, and what I want to talk about here is how aquifers are recharged and contaminant pathways. And the take-home message, if you don't mind me giving it away up front, is that the, the answer to the question is the recharge areas are the contaminant pathways. This way that contaminants get into an aquifer is the very same way that water gets into the aquifer. So when we talk about protecting recharge areas, we're mostly talking about protecting those recharge areas from contamination. All right, so let's talk about percolation processes first. You'll remember that percolation, as we defined earlier in the semester, is the process of water infiltrating beyond the root zone down to the water table and becoming part of the groundwater. Infiltration is the infiltration of water into the shallow part of the soil system where it can be used by roots. Some of it will flow laterally towards streams and join the stream through shallow surface subsurface through flow, and then some portion of infiltration ultimately percolates to the groundwater. All right. Well, the idea here is that, as we talked about in this land use hydrograph several times in several lectures, that land use affects hydrographs because different land uses impact the water shed factors and their interplay, which we also have talked about quite extensively in previous examples. So what I want to come over here is to study this figure on the left side of the slide. And first of all, they've given some example percentages here for each of the different land uses, sort of a forested land use, a very sparsely populated residential area, maybe a suburb, and a full-on big city. Don't worry about the absolute percentages shown in this figure. The point is that land use affects the rate of percolation, the rate of recharge to groundwater, to aquifers. So what we see here is, in our forested setting, we have a certain percentage of evaporation, some runoff, some shallow infiltration through the soil, and then what they call deep infiltration is what we would call percolation to the groundwater. And there we get about 25% getting down. Once again, don't worry too much about the absolute percentages. Those will vary in different watersheds with different watershed factors wherever you're at in the world. But as we move to more and more and more impervious surface in our watershed, more houses, roads, roofs, that kind of thing, we reduce dramatically the amount of percolation of our water, our groundwater, our aquifer. In other words, we're starving the aquifer. We are not recharging it any longer. So if we keep sucking water out of it for human consumption, eventually we would use up all of that water. All right. Infiltration versus percolation. We covered that. This is just a review slide to remind you to pay attention to these concepts. Make sure you know the difference, and that percolation is all the way to the water table, water becoming part of the aquifer, and infiltration is into the soil, and lots of different things can happen to it from there, including percolation. All right, so recharge and wellhead protection. Wellhead protection is something that's gotten a lot of interest over the years. What that is that's protecting recharge areas. So let's look at this diagram on the right from the Phys Rig manual. And we see it's sort of a watershed, typical watershed. We've got different land uses, agricultural, forested, sort of savanna or prairie here, some lakes, some streams. Where's the recharge area in this aquifer, and which part of this aquifer is vulnerable to contamination? Which part of this watershed is vulnerable to contamination that could contaminate the aquifer ultimately? So the first question, where is the recharge area for the groundwater? Well, the answer is everywhere, right? Anywhere that it rains here, the water can infiltrate from the surface straight down to the water table. We'll come back to that in a second, but let's talk about influent versus effluent streams. The other way to think about this is arid areas versus humid areas. So a humid area would be like Missouri, most of the Midwest, most of the eastern U.S. Most of the U.S. west of Missouri would be considered arid or semi-arid, so drier. By the time you get to the southwestern U.S., Arizona, and New Mexico, you've got full-on desert in some places. In arid areas, we tend to have influent streams. So these are streams that actually lose water into the aquifer. Right, so you see the water table here sort of decreases in elevation away from the stream because the stream has water infiltrating through the stream bed or percolating through the stream bed into the groundwater. On the other hand, a gaining stream, like we have in humid areas, effluent streams, the water table actually slopes down to the stream, indicating that the water table is feeding water into the stream to sustain base flows. So, where's the recharge in these two systems? Okay, so you can even pause the video for a second and think about this, but think about where does the recharge, what's the recharge zone of an influent stream reach versus the recharge zone of an effluent stream reach? Well, in our influent stream reach, the recharge area is the stream, right? So if the stream water is contaminated, well, the stream water is what's recharging the aquifer, and the recharge zone is going to be water moving from the stream into the aquifer. Now, on the other hand, in a gaining stream, the recharge zone is the whole landscape except for the stream. Anything that happens on the landscape, any water that percolates will eventually come out in the stream. And the contaminant pathways are similar. If we think about where's the contaminants come from in these systems, well, mainly what we need to protect in an influent stream reach is the stream itself, because if we get contaminants in our stream water, that stream water is recharging the aquifer will become contaminated. On the other hand, in our effluent stream reach, any contaminant that comes across the surface of the earth, oil leaking from a gas tank, or gas leaking from a gas tank, or oil spilled on the ground, or some chemical spilled somewhere, it's going to infiltrate through the soil, and some of that could percolate and contaminate the aquifer, which will eventually contaminate the stream. If we have a spill directly into the stream in this system, well, the stream is just going to flush that downstream, and it'll be somebody's problem down there. But it's not going to affect our aquifer because water's moving from the aquifer to the stream, not vice versa, like it is in an influent stream. So when we talk about wellhead protection, we're talking about protecting the portions of the watershed that are vulnerable to aquifer contamination. In an unconfined aquifer, such as the one shown here, and we'll define unconfined and confined later, but for now, in an unconfined aquifer, everything in the watershed except for the stream, every square foot of this watershed is a place where a contaminant can infiltrate and eventually percolate to the groundwater and then be discharged into the spring or into the stream. Let's talk about the significance. So contaminants can come in many ways. I've given a couple examples. Here we have a pile of dead chickens that have been improperly disposed of on the land surface. As those decompose and the fluids and all the other yucky stuff seeps into that soil, if there's groundwater under there, which given the lush vegetation behind that, there probably is, that water is going to infiltrate through the soil. It'll get to the shallow water table and it's going to contaminate that. If we blow up this figure on the right, we have a cartoon that shows an urban area, an agricultural area, residential area, and we have both recharge, the small arrows here, percolation down to the water table, but we also have contaminants, maybe the bigger blue arrows here, where we've got a leaky septic tank. That leaky septic tank is sinking into untreated sewage, essentially, seeping down into the water table. We have runoff from this feedlot, manure and urine from all the cattle infiltrating and percolating to the water table, and then all the stuff that comes off an urban area, oils and hydrocarbons from roads and industrial and manufacturing discharges and so forth. And all of that eventually makes its way to the water table and then flows towards our well over here. And when we pump water out of this well, we're not just getting the water, we're also getting the contaminants. Now, one thing you want to keep in mind is, if you live out in the country, you probably have a septic tank and you probably have a private residential well. You always want to make sure that your well is upstream of your septic tank. Think about this. If this were the well for this yellow house, they're pooping over here. That poop is not being properly treated. It's contaminating the water table and flowing straight into the well, which then they pump out and drink. Do you want to drink that? Probably not. If their well were over here on the other side of the house so that it were drawing out of the aquifer upstream of the contamination, then they would have maybe cleaner well water and they would just be contaminating the neighbor's groundwater. Doesn't really seem like a problem to most people, I guess, but it probably is if you're the neighbor. All right, so we'll end that there and we'll continue our groundwater lectures. In the next lecture, we'll finally define what unconfined and confined aquifers are. I'll see you then.